Thanks to everybody for inviting me to speak in this SESTA seminar. I wish I were there in person, but that's not the case this time. Next time, I always enjoy getting out to Stanford area. So, all right. So as Eric said, this talk is about the role of information access and inclusion in visualization. And I'm being very broad here in terms of how we're thinking about visualization. This can be scientific visualizations, it could be artistic visualizations, environmental visualizations, et cetera. And so my goal today is to consider limitations of current visualization approaches and to discuss best practices for improving how we can visualize data, really of all types, in order to, one, increase its learning and understandability, two, to increase inclusion of the people who consume it, and three, to really better mirror how the brain itself performs data visualization and data processing. Note that there is a lot of science underlying the stuff that I'm talking about today. I'm really, given time constraints, not focusing on specific data. I think it will be more helpful for me to kind of give a high-level idea of the concepts. And I think this will hopefully generate some of the subsequent discussion that we're going to have. And then I'll also end with some specific examples that I'm going to be talking about. Finally, just as a little bit of background, as a blind guy who got my PhD in a vision science program, and now who works in a spatial computing program focusing on multi-sensory access, you know, I guess I bring somewhat of a different perspective to the norm on the role of visual information, the role of visual perception in the tools that we use in the visualizing process. That's some of what we'll talk about. You know, the conventional approach for communicating numeric data or graphical content, whether it be abstract or concrete, involves using different visualization techniques. So we use things like diagrams and figures and animations and the like. So a major theme of this talk is that most of these approaches, I'm arguing, are outdated in terms of their etiology, which we'll talk about, and understanding of human information processing and the technology used. And so, you know, we'll talk about some of the specifics, but the aggregate result is that much of what is used in current practices today is exclusionary to many of the people that are trying to use it, and it doesn't maximize the brain's native abilities for communicating information. And I argue that this is a problem. So an alternative approach that I'm advancing here argues that numeric and graphical data representations and the technologies that we use to visualize them really should be designed based more on how the brain operates. So essentially using multisensory information and interactions. And the result of this, what I think of as a bio-inspired kind of multisensory approach, is that visualizations will be more intuitive, they'll be more realistic, they'll be more inclusive. And those are important. One second note I want to make before we get too much further, although a lot of the talk that the things that I'm going to talk about today are geared toward information access for blind and visually impaired people. You know, this is a focus of a lot of my research. There's some personal interest here. Inclusive design is by definition independent of any ability or disability. And so in other words, improving access to blind folks also increases inclusion and equity to everybody. And that's really the goal of universal design. Oh, my slide didn't advance before. I apologize. Oh. All right, it's giving me, computer's wanting to screw with me. That's all right. It thinks it's the end of the day. We're 3 hours earlier there in Stanford, buddy. All right. Nothing like anthropomorphizing your computer. So some problems in positions. And I've kind of structured this talk around some problem statements that I'm going to argue underlie a lot of the issues that I'm talking about. And then they're going to be followed by some related positions and some hypotheses that that I think not only kind of support my views, but importantly serve to guide us moving towards some solutions. Okay, so my first problem statement here, P1, is that most of the tools and technologies and terminologies used to perform or to talk about visualizations are based on a misconception about the visualizing process. And that is, whether it be, data visualization or visualization of a process or a design or conceptual visualization or what have you, the mistaken belief is that this is about vision and visual information. And, at the end of the day, this confusion is understandable. I mean, we can't even write or say the word visualization without including vision. But I argue that this is really far too literal, and it leads me to my first two positions. So P1 here is characterized by the following hypothesis. The majority of what most people call visual information isn't really visual, but it's actually spatial information. And I don't mean outer space here, but I mean spatial relations, the spatial relations around us. So it's kind of a quick thought experiment. I want you to think about the room, wherever you are. Think about the room that you're in. And my question is, what is intrinsically visual in what you are seeing? So, color is fine, texture certainly is, but think about things like 3D structure of space, the relation between edges and surfaces, the direction and distance between objects and people. These things are spatial properties, and they can certainly be specified through vision and very well, but they also can be specified through other spatial channels. So touch and haptics, which is active touch, audition and hearing, and spatial language being the most notable. Okay, so this brings me to my second position, which kind of builds directly on the first, but ties more explicitly to visualization. P2 argues that since the vast majority of visualizations rely on visual information, and since most visual information is spatial information, then it follows that most visualizations are actually conveying spatial information. And again, think about numeric representations and data graphs and figures and diagrams, photos, maps, 3D renderings, what have you. These, and similar to the room example, these things are all mostly about the relation of spatial information, spatial relations, spatial configuration, and are best described directly using spatial concepts rather than visual concepts. So the previous two positions motivate a second core problem for data visualization. And that problem is that most visualizations rely only on the visual channel for conveying information, kind of a natural extension. So this leads me to my third position. Position 3 argues that since the brain processes spatial information from all of our senses, effective visualizations should also be multisensory. In other words, they should use multiple channels of information delivery to convey that spatial information. So I'll discuss more on specific benefits of multisensory information in a bit, but the bottom line is that while vision is a great conduit of spatial information, it doesn't have a monopoly on space. All of our senses, as I just mentioned, convey spatial information and in a very compelling way, as we'll talk about. And so you can think of space as kind of the common denominator of the senses. And I admit that I come back to this a lot. I'm kind of a skipping record because I think it is really important for driving the point that I'm making here. So let me talk briefly about some underlying theory, because I think this is important if you're to accept my arguments about why we need multisensory visualizations and why they work. So there's now results from a growing body of converging research, behavioral, neuroimaging, computational, and they converge to demonstrate that there is far more similarity than difference in how multisensory information is processed and represented in the brain. And over the past bunch of years, I've studied this idea with a number of colleagues based on what's called the functional equivalence hypothesis of spatial information. And that's kind of a long name for a kind of simple argument, or explanation. So what this is saying is that spatial information learned from different input modalities, whether it be audition or touch or vision or linguistic, what have you, it leads to spatial understanding and spatial behaviors that are statistically identical, or what you could think of as functionally equivalent, independent of what sense was used during the learning process. And so we think about this in terms of an example. I have a simple three-leg route map here. And imagine that I asked you to learn this map, and I asked you to do it from vision or by feeling it. If you develop functionally equivalent representations, then you should be able to do things like, well, pointing between remembered locations, or if I asked you to recreate the map, or various other tasks. You should be able to do this with similar accuracy, irrespective of how you learn the map. So if you learned it from vision or touch. And it turns out that this is true. There's a lot of data that I could show you. There's some of it, if you're interested, shown in these references that are shown here, but this turns out what is the case. So this brings me to my fourth position. Position 4 argues that the robust evidence supporting functional equivalence is best explained by what we call the amodal hypothesis. And the bottom line, essentially what this means is that spatial information from different inputs used during learning builds up into a unified amodal, or what you can think of as a sensory independent spatial representation in the brain, which is not tied to that input source. And so therefore, functional equivalence occurs, and why we're finding this data is because our computational and cognitive processes and the behaviors that they're supporting, they're essentially tapping this unified representation that's guiding our mental interpretations and our physical actions. We call this amodal 3D representation the spatial image, and you can see in this conceptual block diagram here, kind of how this would be represented in the brain. So at this point, you might be saying, Nick, what's the relation here? You started talking about visualization, now you're talking about functional equivalence and amodality. How do they all connect? Well, the bottom line is that this basic research on functional equivalence speaks directly to the ability of humans to not only effectively learn using non-visual information, but also that doing so supports the same level of mental understanding and behavioral performance as is possible when learning from visual information. And this equivalence, it's important because it provides a theoretical framework and empirical validation for why communicating spatial information using multimodal approaches works, and why it's important for our visualizations. There are many advantages of using multisensory interfaces, but my key take home, if you don't remember anything else, is that interface design, and especially visualizations that we're designing and using, should borrow more from what our brain does so well. We are amazingly good at seamlessly integrating multiple channels of information into a unified experience. That's how we perceive the world. So let me bring this from a high level to some practical, kind of tangible examples. What are some benefits of multisensory interfaces in design that we can think about for visualization? Well, first, they optimize the brain's ability to integrate, process, and act on spatial information. So in other words, for visualizations to maximize efficiency in what and how information that they're going to be communicating, we should complement the visual content with multiple sources of non-visual content. Second, designing visualizations to be inherently multimodal and using redundant channels of spatial information just represents good inclusive design. It's going to benefit the greatest number of people. So we have, people with disabilities, you have people of different ages, you have people of different learning styles, really everybody. We all, at the end of the day, are multimodal learners. We use all of our senses. Otherwise, we would have evolved with just vision, and that's not the case. Third, and perhaps the most obvious, using multimodal visualizations is most consistent with how we actually perceive, experience, and interact with the world around us. We use this kind of rich mosaic of multisensory information, and so should our visualizations. So with all this in mind, why are so many visualizations still based almost exclusively on vision and visual information, and largely ignoring what has been learned from the most powerful information processor in the world, our brain? I mean, the brain, as we just talked about, is better than any computer, even little tiny mouse brains, at simultaneously perceiving, processing, and representing information from multiple senses. The bottom line, we've done, I guess I'd say we've done a poor job of connecting what we know about the brain and from neuroscience and other aspects of multimodal learning with how our visualization techniques, actually work. And the reality is that the vast majority of our visualization approaches and the technologies that we use still are limited to simple interactions like, typing and tapping and finger gestures for data input and manipulation, maybe moving a mouse around, and then visual displays for data output and presentation. And this is silly. It's not how we actually experience the world from all of our senses and all of our sensory channels. There's lots of reasons why this is happening. Partly it's because visual interfaces provide the most bang for the buck. We can do a lot with doing something just visually. It's also due to an inertia problem. It's essentially based on what's worked in the past. And kind of a big and related to that, a big explanation is due to basic human nature. People resist doing new things, especially if what they're currently doing works good enough. This brings me to my final position. Position 5 argues that good enough doesn't cut it anymore. Our visualizations need to adopt new bio-inspired approaches for conveying information based on how the brain performs multisensory input and output functions. And this is frequently talked about. You hear this a lot in the importance of multisensory and multimodal, and there's lots of benefits. We've discussed some of them, but the reality is that there's little actual progress that's been made. Some, but not a lot. And so when I was writing this, I thought back to my grandmother. My grandmother used to tell me when I was procrastinating or equivocating on something, and she'd say, "Nikki, do your business or get off the pot." She wouldn't actually use that voice, but sorry, Graham, I'm trying to get the message across. It's a good point, and that's what I am trying to do here. So, as I said, there are some really good examples and some promising tools in the visualization domain that are doing what I'm talking about, and specifically virtual reality and augmented reality technologies. There's lots of variants here. Many of you may have used some. You can use monitors, you can use head-mounted displays, you can use caves, you can use augmented reality and smart glasses. The advantages of this technology for visualization include, they're based on realistic 3D simulations, which makes a big difference. This makes them highly immersive and believable. They allow people to move in three-dimensional space and have three-dimensional interactions, which are very realistic. They support the ability to model and simulate any type of multidimensional data. These are all important things. What I'm particularly excited about is that this technology is finally moving from vision-only interfaces to using multimodal information. So, this is important because historically, virtual reality was synonymous with visual reality and visual simulation. That's all you'd get, maybe a tiny bit of audio. But this is now changing. So for instance, VR systems now, and you can experience these in many places, they're starting to use spatialized audio. They're starting to use touch and haptics. You get some temperatures and even taste and smell in the simulations. And this is great. This benefits. Using these types of multimodal cues increases VR's inclusion to people who can't see and who have different disabilities. But really, it just is it just improves its realism and makes it more impactful and more immersive to everybody, because now we are modeling how the brain actually works and how it processes and interprets, and how how we use multiple sources of information. And having this in our simulations is really great news for information visualization of the future. And I'm excited about where this is headed. Okay, so I'm going to now quickly discuss a few research projects in my lab that are based on multimodal bio-inspired visualizations in a couple of different domains. Okay, so there's currently over 12 million people in the US with some form of uncorrected vision loss, and this balloons to 285 million people worldwide. So we're not talking about a tiny demographic. And most of these people have trouble accessing visual graphics of whatever type. It's just there's no current easy and automated and quick way to convey graphical content non-visually. And just as a thought experiment, that's easy to say, but think about how much graphical content of any type you use throughout your day, whether it's at work, whether it's social media, or what have you. What would you do if it suddenly was not available? This would absolutely change a lot of the ways and interactions that you have. So our goal in this project and this whole kind of line of research was to develop new multimodal visualization techniques for accessing graphical content. And we're focusing specifically on STEM here because this is a big part of education and a big part of workforce success that's highly reliant on graphical content. So our solution uses the touchscreen of smart devices, so phones and tablets, to communicate graphics and numerical representations through combinations of touch, audition, high contrast vision, and kinesthetic cues. So you may say, well, Nick, I don't quite get it. You're talking about using touch and tactile cues on a flat glass touchscreen. How does that work? It's totally flat. Well, good point. But what we realized is that the embedded vibration motor, which most people use as kind of a tertiary cue that your phone might be ringing, actually works amazingly well in generating tactile sensations. And these are called vibrotactile stimulation. And how it works is that whenever an on-screen visual element is touched, predefined vibration patterns are triggered at that screen location. And so the result is that the people have this perception of feeling vibrating points or lines or regions that is really quite compelling. And so where traditional paper-based tactile renderings, which is the current gold standard for haptic visualization, are static and they're only touch-based, our solution is dynamic, and it provides this kind of robust multisensory visualization experience using these different senses that are synchronously and simultaneously working together. We call this a Vibro-audio interface. Okay. So we've now done a lot of research in the lab with this visualization tool with really promising results. Again, there's some citations you can check out, not getting to the data, but I can say that, we are very excited here. So some of the things that we've been looking at are evaluating the efficacy of this VI, or the Vibro-audio interface, for learning things like maps and figures, kind of large scale, complicated images, and also more common data representations like bar and line graphs, pie charts, and Venn diagrams. And the reason that I'm so excited about this approach is that every study that we've done, and we've now run hundreds of participants, has shown that the VI system that we've created is equivalent to or better than all current non-visual rendering techniques. And so, the difference is that unlike these traditional approaches, the VI has the benefit of being dynamic. It has the benefit of being multisensory. It's portable, and it's implemented on a smartphone, which is the preferred computational platform of almost all blind, or the vast majority of blind users that already own and use. So, of all my accessibility work, I've worked in this field for 20 years. I am most excited about the promise of this technology for improving information access and multisensory visualization. And we've also published several design guideline papers, which I'm really excited about because they kind of take the research and dovetail it into very specific guidelines that people that want to use this technology, other folks around the world that are interested in using the VI, can use to make sure that their visualizations are perceptible and optimized for this interface. Another visualization domain that I've been interested in uses what we call compensatory augmentations. And this involves using augmented reality to compensate for key environmental features that people cannot see or people that have trouble seeing through strategically placed multisensory augmentations that make those features more salient. So in other words, we're doing things like superimposing high contrast virtual edges or lines on low contrast cement benches in the environment to make them more visible. And the goal here is to draw the user's attention to these elements during navigation specifically, and therefore providing alerts about potential hazards or drawing their attention to features of interest. And these compensatory augmentations represent visualizations with enormous potential to benefit older adults. So, people over 65 have the greatest incidence of vision loss, and particularly in things like reduction in contrast sensitivity and visual acuity, but they still have usable vision. Similarly for low vision people, so a lot of people don't realize 90 to 95% of legally blind people still have some functional vision. And so the compensatory augmentation that we're using are on smartphones. They use the smartphone camera, or these could also be done on smart glasses, and they employ real-time computer vision and machine vision algorithms to detect key features or objects in the environment that have been previously trained using a neural network model that's essentially used to learn and classify these objects of interest. And so the system then can detect anything that's been learned, and it can do things like put high contrast lines on the features, or it can put bounding boxes, high contrast bounding boxes around the features of interest. And this is useful because these things because they're high contrast, are usually very visible and to older adults and people with low vision, and therefore can be very useful in drawing attention to them. Now they're seeing these through the phone, which is why it's an augmented reality situation. And by looking through the phone, and they're able to see these environmental features. We call these multisensory, as once detected, we can also speak the object's name and use spatialized audio and vibration cues to indicate its direction and also its distance. So if we're using distance is a little bit more difficult, but if we're using things like LiDAR, which a lot of cameras have, or new phones have, we're able to get that. And so this means that the same augmentations can be used for someone with low vision as someone with no vision. So just again, we're aiming for good universal design in multisensory interfaces. This project looked at using the compensatory augmentations that I just talked about to prevent falling by older adults. So you can think of this as an environmental visualization. To set the stage a bit, accidental falls represent the leading cause of fatal injury for people over 65. So it's something like over 20,000 people a year die because of falls. More than 2 million people annually have hospital visits because of falls. And in 2020 alone, falling led to over $67 billion in medical expenses. So this is a big deal. The early stage project that we're looking at here is aimed at reducing falls by visualizing the highest probability parts of the environment that actually cause the fall. So for instance, low contrast elements that are difficult for older adults or low vision people to see, and especially during navigation. So things like stairs, things like curbs, bumps, or any type of elevation changes in the sidewalk. And so here we're superimposing high contrast virtual lines on the stair facings or on the edge of the stairs and providing redundant auditory labels to help direct the user's attention to the stairs when they're detected. And this is just a prototype, but it's very promising. We know from the literature that people fall far less when their attention is drawn to the potential hazard with high contrast paint. And you see this on the edges of things like train platforms and some new stairs. You'll see these high contrast platforms. And so the reality is, if we could run around with a paint can and spray the edges of steps, that would be fine and that would work, but that's not going to happen. And so our goal with these different compensatory augmentations is to provide a low-cost, real-time solution that improves navigation safety and efficiency through these targeted environmental visualizations. So these compensatory augmentations are focused on conveying information about the environment during navigation that could be useful. So instead of hazards, people also want to figure out where stuff is. And so in these, we're putting high contrast bounding boxes, the virtual bounding boxes, around objects of interest. So in this case, we've trained with light switches, with exit signs so people can find where the door is, coffee mugs because I'm always losing mine, and that seems like something that people are often having trouble finding. But you could imagine doing this with lots of different types of objects. These augmentations are being developed as part of work that we're doing on improving the accessibility of autonomous vehicles. This is another big area of my research, and there's a huge amount of issues around autonomous navigation, but also some huge benefits to blind and older adults. And so these examples are aimed at supporting blind individuals and older folks in navigating to the vehicle when there's no longer a human driver to provide assistance. And it turns out this is a huge problem. If you have your autonomous vehicle show up and there's no one there to give any input, there's a lot of problems that occur. And so our focus here is on hazards. And so this figure here is showing me walking, holding the phone, running the compensatory augmentation app. And once the system detects these orange construction cones that are in my path via the camera, it says their name, it vibrates the phone, and it superimposes a high contrast bounding box on the objects. And as I move the phone around, I can determine information about the object's direction. And as I get closer, I get information about its distance. These figures are just showing some other objects that we have trained the system to detect from various orientations. So this is including hazards like guy wires and overhanging branches. These are particularly dangerous for blind people, as canes and dogs are really good at detecting objects on the ground, but they're not really good at anything that's chest level or above, and these can be really dangerous. I've knocked myself flat by hitting guy wires before, and so this would give that information as someone's walking. We're also training with door handles. So when autonomous vehicles hit the road and they're going to be out there and they show up as a ride-shared model, which is how they're expected to be used, the user will be able to identify the vehicle and also to figure out where they need to enter. Compensatory augmentations can also benefit distracted sighted users. So we call this situational blindness. So think about how often that you've noticed somebody walking around, texting on their phone, and running into a post or falling into, this case, falling into a manhole. This is something that happens all the time because people are distracted. So in this project, we're using the same concept. We're using the computer vision algorithms in the camera to monitor the environment and to provide vibration and auditory cues to solicit the distracted user's attention when they're about to run into something. And you can imagine lots of other applications where situational blindness situations come up and it would be useful. All right, I'll finish by summarizing a few take-home points that I'm hoping you'll leave with. So first, we need more bio-inspired visualization approaches based on the brain's playbook for natural information processing. Second, we need to move beyond the vision-only bottleneck of visualization to support use of multisensory input and multisensory output channels for presenting and communicating information. Third, we need to design visualizations using technologies and techniques that serve as many people as possible. And this inclusive design should be done from the beginning, not as a post hoc Band-Aid, which is all too often the case. And fourth, didn't talk about this much, but I think it's really important that we need better crosstalk between scientists and engineers and technology developers and end users, all these people that are using visualizations, because this collaboration will really drive better and more inclusive visualization design and usage in the future. I have a lot of collaborators and a lot of people that have helped to make this research happen and funding sources, and I want to thank them here.